Hi everyone, today we're going to talk about this paper titled A Careful Examination of Large Behavior Models for Multitask Dexterous Manipulation by TRI-LBM team. This is honestly one of the most rigorous robot learning papers I read when it comes to reporting, training, and evaluation details, so I think their findings are really credible. Professor Rose Tadrick also presented this work in the Stanford seminar series, which is on YouTube, and I highly recommend people to watch it. With that in mind, I want to walk you through some of the key takeaways I learned from this work. On a high level, this paper investigates large behavior models, or LBMs, for multitask dexterous manipulation, asking whether large-scale pre-training and scaling can unlock generalizable robotic skills. On the pre-training side, the results largely align with the thesis that large-scale pre-training on diverse data significantly improves data efficiency when fine-tuning for single tasks. Namely, as pre-training data scales, so does downstream performance. That said, there are some caveats where certain tasks actually show statistically worse performance for fine-tuned LBMs than single-task baselines. For their observation and action spaces, they include end-effector poses with respect to the station base frame, and also end-effector poses with respect to the other end-effector, which I found is very interesting. They want the system to be explicitly aware of how the two arms relate to each other in space. And for the orientation representation, they use the 60 vector representation, which is the top two rows of the rotation matrix. And this is an important result from this paper called On the Continuity of Rotation Representations in Neural Networks. And since they are both bimanual and unimanual robots in their data sets, for the unimanual robot data, they zero-pad the missing arms and randomly swapping the arm side, which I think it also makes sense. And when it comes to giving language instructions, they give 5 instructions generated by prompting a LLM, which makes sense because we actually want the robot to get used to different wordings instead of overfit to one single wording of the instruction. And now onto the data normalization part. Firstly, they scale their data by the 2nd and 98th percentile and clip beyond the range -1.5 and 1.5. This is very similar to the Pi 0.5 paper, where they, instead of 2nd and 98th, in Pi 0.5, they do the 1st and 99th percentiles and clip beyond the ranges -1 and 1. Another point I found very insightful is that they compute the normalization parameters for each timestamp independently. And I think this is because that they represent actions relative to the current time's observation, so actions further into the future have a wider spread than the immediate next action. My interpretation of this is that, for example, if you are training a robot to pick up a cup, right after the robot sees the cup, its very next action might be just a few millimeters of gripper movement, which is tiny but very critical because you want to move in the right direction for the right amount of distance. But several steps later, its pose could be anywhere around the table depending on how the motion unfolds. If you put all those actions on the same scale, the millimeter adjustments looks like noise. And by normalizing each timestamp independently, those fine-grained and short-term movements stay meaningful. So now on to the dataset filtering part. In this section, they found some pretty surprising results, which is that filtering the low motion data meaning where the robot is not moving or not moving that much, filtering those data improved single task performance in simulation. But then it actually decreases in performance for pre-trained LBMs. And the failure mode is that the pre-trained LBMs would commit to some uncommanded tasks more often than before. For the single task case, it actually makes sense to me because by removing redundant or uninformative data, it actually forces the model to learn the core motion patterns without getting distracted by still frames. But for pre-trained LBMs, things flip, and the reason might be that the LBMs are trained across many tasks and environments, and those quiet frames actually provide critical context. They teach the model what a neutral or idle state looks like before any action begins. And without them, the LBM loses that anchor and can prematurely commit to a task because it no longer knows how to interpret ambiguous starting conditions. So now on to the evaluation part. Here they mention that the evaluation environments in simulation are designed specifically to be visually ambiguous given their initial conditions. So the policies have to rely on language conditioning to determine what actions to execute. This actually tells us something important to watch out for during training robot learning policies. So if you let the model rely too heavily on the initial scene, it can start exploiting spurious correlations instead of actually listening to the language. An example might be, say in your data set, the cup happens to be closer to the gripper more often than the bowl. So the model might learn a cheap shortcut, which is if something is near the gripper, just pick it up, regardless of what the instruction says. That looks like it's working during training, but in deployment, it breaks down as soon as the distribution shifts. Say now during deployment, the bowl is closer, but the instruction is pick up the cup, and because the model learns the wrong thing, it actually picks up the bowl because the bowl is closer, and that's what the model was learned. That is everything I want to share about this paper. Thank you very much for watching this video, and I do recommend people read this paper and watch Professor Russ Tedrick's talks on YouTube. Thank you very much.